Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and just ask you to bless our work this morning, Lord. In your name I pray, Lord Jesus. Amen. Okay, so today I wanted to talk to you guys about vector spaces, and then hopefully leading to some of the calculations we can do in vector spaces. And so, like we've talked a lot about in here, how to do calculations with matrices over Rn. But let me just give you like a very brief definition. So V is a vector space if over F. If V is a set with an addition and a scalar multiplication. So like in particular for x and y in V, we need x plus y is in V. And for C in the field and x in the vector space, we need C times x is an element of the vector space again, right? Now here, this is a field. What's a field? Well, a field is a set of numbers which allows addition and multiplication in the usual sense, associative, distributive, commutative, and also every non-zero thing has a multiplicative inverse. So examples of fields that you've heard of: rational numbers, real numbers, complex numbers, but there's other stuff like Z mod P, where P is a prime, and etc. So like the etc. I will leave to Math 422 mostly, but basically there's infinitely many different choices for what your field is, right? Like there's tons and tons of choices here. So this semester, for the most part, we have worked almost exclusively in this category, right? We've worked with real matrices. We did dabble a little bit in complex, right? But it was kind of a passing thing. So what are some examples of a vector space? Well, you could do like m by n matrices. M by n matrices, this is a vector space, because if you add two m by n matrices, guess what? You get another m by n matrix, you know? But of course we could bump it up a notch. We could do this over any field, right? You could look at matrices over any field, and you'd still have a vector space. We don't really care that much about that today, so I'll drop that off the list. You could do things like linear transformations from one vector space to another, right? Because, and by the way, we can extend our notion of linear transformation to be, like this. So T going from V to W, what's it take for it to make it a linear transformation? You have like T of x plus y is T of x plus T of y, and T of Cx is equal to C T of x, right? These two rules for all x and y make T a so-called linear transformation, all right? Man, what else is there? Well, basically, if you take any set of functions, going from some set to a vector space, actually, is a vector space. So any set of functions. So here I just mean like the set function that goes from some set S to W, such that W a vector space. This itself is a vector space, because if you add two functions together of that type, you get another function of that type. And we can scalar multiply the function. As long as the range, well, rather the codomain of the function is a vector space, this all works together. So this is just a couple of examples. Actually, these aren't really specific examples. These are examples of examples. there's obviously like an infinite list of these things, right? And in any of these examples, we have vector addition, we've got scalar multiplication. So we can do things like, you can study a subspace, right? We say W is a subspace of V if W is a vector space with respect to the operations of V. All right, so this is definition of a subspace. A subspace of a vector space is a vector space inside the vector space with respect to the given operations. So we've studied subspaces in here some, right? But all the subspaces that we've studied in here have been what? They've been subspaces of Rn, right? We studied column space, null space, right? We talked about for a given subspace of Rn, we could calculate the perp to that space. Remember these things we've all studied in here. We've studied eigenspace. That's another example of a subspace, right? Because the sum of eigenvectors is an eigenvector. But my larger point here is if we continue our study to the study of vector spaces, we also want to study subspaces. And you know, in Math 321, one of the first things we'll talk about is the theory of subspaces and how you can categorize a subspace a couple different ways. Like one is by the subspace test, the other is by the span theorem. The span theorem simply says that you know, the span of any set of vectors is a subspace of V given S is a subset of V. So anytime we take all possible linear combinations of some subset, that forms itself a subspace. Right? Now, one of the, you know, and then we also study the theory of dimension for vector spaces, right? The dimension of the vector space is equal to the cardinality of the basis of the space. Here V being the span of beta and beta linearly independent. So the cardinality of a vector space, it doesn't have to be finite, right? Like the dimension of Rmn, what do you think that is? This is literally the span of Eij, 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N, right? So count those things, those are linearly independent. The matrices that have 1 in the ijth spot and 0 elsewhere, those are linearly independent. They span the whole set of m by n matrices. If you count, you can find out that the dimension of the matrix vector space is simply Mn. All right? And it turns out that the dimension of the linear transformations from V to W is also Mn if we know that the dimension of V is n and the dimension of W is n. All right, so there's a, and then like the deeper discussion in vector spaces is we talk about isomorphism. When are two vector spaces the same? Well, it turns out that finite dimensional vector spaces are isomorphic if they have the same dimension. They're essentially the same set in a different notation. All right, so on the other hand, things like this, all possible functions, this could be infinite dimensional, all right? And that's one of the things I'm going to show you guys today. We're going to look at some infinite dimensional vector spaces, all right? So I just wanted to give you a quick lay of the land, all right? This is what basically what we study in Math 321 is an abstract vector space, the structure of it, linear independence, spanning, what you can say about dimension, what you can say about linear transformations, everything we've done in this course, except instead of just looking at column vectors, we look at, you know, what's the word? Abstract vectors. But the cool thing is if you can prove a theorem, for vector spaces, then you have proved that theorem for all of these examples, all at once. And that is the power of abstraction Well, eventually my computer will wake up. Stop breathing?
Yeah.
Well,
Cure to sneezing.
You know, that's true. The best way not to die is not to live.
That's true.
See here, death is the number one cause. Living is the number one cause of death, I should say. It's here.
I think everybody who's died has drank water at one point.
Few know this. Oh, drinking water?
Yeah.
I guess I can imagine a world where no one drinks water. But,
What would the water be replaced by?
Sparkling water.
well, sparkling water?
Just the bubbles.
In the Sprano version, it's just all Mountain Dew all the time, or Diet Mountain Dew, possibly.
We're in a world, instead of breathing oxygen, we breathe those bubbles. You know, what is it,
Carbon dioxide?
yeah, the carbon, is it carbon dioxide?
I'm pretty sure that's what they carbonate it with.
Yeah, carbonation.
Oops.
Breathe the carbonation.
Sorry guys, I'm in the wrong notes. I gotta. Give me a second here. I thought I had everything open for today, but I forgot to open this. All right. Now, so guys, the other thing that gets abstracted, in addition to just what a vector is and all that, is the notion of distance and length and so forth. So the other thing we talk about a bit in 321 is what's a geometry. Like a linear geometry is a vector space paired with a notion of an inner product. And so we've studied a little bit about the Euclidean geometry of Rn, because we use the dot product to define orthogonality and all that, right? But there are other notions. There are other notions beyond that, which I'll get to eventually here. These things we've done here. Come on. I will eventually get to it.
Okay.
Eventually.
Oh, again.
Inner products, yay! All right, so here, what is an inner product? If we have a vector space, warning. All right, well, I put a warning on this section. Oh my goodness. All right, so these notes are still from from a different time. They're really from Math 321 as it used to exist, which no longer is the case because this course exists. So anyway, so an inner product, we use this notation. So in LaTeX, this is Lengel and this is Rengel. So bracket and bracket. So this is a notation for an abstract dot product. All right, so like the inner product, as it's called. And the properties of the inner product is that it has to be symmetric, it has to be additive in the first slot, you have to be able to pull constants out of the first slot, and positive definite. Now this is the definition of a real inner product. Technically speaking, a lot of times people are working in a complex vector space, and the definition for a complex vector space is a little bit different. So we'll talk about that in Math 321 as well. But anyway, if we have an inner product, we can talk about what it means for vectors to be, perpendicular. So like, just drawing back to my examples over here, in our m by n, for example, or let's say n square matrices, just to keep it a little bit, if A and B are elements of our n by n, then you can define the inner product of A and B actually to be the trace of AB transpose. That gives us a notion of inner product of matrices. If we're dealing with functions that are continuous on the interval of 0 to 1, then if you want to take the inner product of f and g, you simply integrate from 0 to 1 f of t, g of t, dt. So these are examples of inner products. All right. Now, this is just like a super slick way of writing out the following formula. A11, B11 plus A12, B12 plus dot, 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 ANN, BNN. So like, this is the so-called Frobenius inner product. And it just amounts to taking the matrix and like listing it out as a giant, did I do m's? Oh, n, a giant n squared dimensional vector. Like if you just take the matrix and just lay out the columns one after the other, or rows, you'll get a giant vector, right? And the Euclidean dot product of that vector with its corresponding other vector is simply that. So like this is just a slick notation for that. But anyway, but once you have an inner product, you can do things like define an induced norm. The induced norm is simply defined by the square root of the inner product of x with x. So that has the properties of a norm. Properties of a norm are the properties of vector length that you've seen this semester. It satisfies the triangle inequality. You know, if you have a constant times x, it pulls out as the absolute value of the constant times the norm of x. What else? You've got the norm of a vector is 0 if and only if the vector is 0. These are other properties of norms. So the properties we saw for vector length, for the length of a real vector, they're all also properties of the abstract concept of a norm. Here they are. So like, you know, the vector length is non-negative. We can, 0 only if it's the 0 vector. What else we got here? Pull out the constant. And sorry guys, I'm just making sure I get something in camera here for the sake of those who aren't here. So like the larger thing I'm saying is that everything we've done for Rn, whether it's addition, linear independence, spanning, or even notions of geometry, they all have analogs in the theory of abstract vector spaces. And that in a nutshell is what Math 321 is about. It's about trying to do what we've done this semester, but in the most abstract way possible, given a semester's time. So over here, I have the distance function. The distance between 2 points in the vector space is given by the difference of the norm. So the distance between 2 points is the length of the displacement vector between the points. Right? So we can define a distance between points. We can define orthogonal complement for inner product spaces. Like if I have an inner product, then the orthogonal complement of W, which is a subspace, is like all V in the vector space, such that, oh man, that should be inner product of V and W. My Euclidean geometry showing here. Oops, this should be like inner product of V and W. Oh man, that's so sad. Anyway, I need an editor. Let's see here. These are the properties of the inner product for, an inner product space. Like if the inner product of two vectors is 0, we say they're orthogonal. The length of x plus y squared, length of x squared plus length of y squared. Hey, you recognize that, right? But understand that I'm not talking about the dot product here. I'm talking about, it could be this or it could be that, right? These more abstract notions of distance, but there's still the theory of orthogonal complements. Now, I think to be fussy, I really do need finite dimensionality to be sure about these. I'm not so sure this holds in the infinite dimensional context. I'd have to think about that for a minute. I don't trust my notes here on that point. These notes were written with a finite dimensional bias to start with. So that's one of my other pet projects in Math 321 at the moment, is trying to make it as infinite dimensional as we can stomach, given the level of the course, which is more than you might think. But anyway, so if we have an inner product space and we have an orthonormal basis, what does an orthonormal basis mean? You have a basis which are pairwise perpendicular, and the length of every vector is 1, right? If that's the case, then we have the ability to write the vector as a linear combination of the projections of the vector onto the v1, onto the v2, onto the vk, and it's a sum of its projections onto the respective, k-fold vectors in the basis for the w. And of course, we can project onto the subspace with this formula in general for a general vector x in the vector space. And we can find the piece which is outside the subspace by subtracting off the projection. All these things should be familiar, but please understand that I'm not necessarily writing these formulas just for Rn here. This is all for like an abstract vector space. So there are some rather unexciting examples of abstract inner products. The one is you can just take R2, just the plain old plane, and replace it with a, oh man, where's my other laser? Oh well. I guess we're just going to be blue today. Yeah. Put it in my pocket. No. All right. So here we go. So why do you think you might look at a inner product like this? I don't know. Maybe your inner product has something to do with like grades or something, and the second assignment is worth more than the first, like 3 times as much. Maybe you do something like that as like a weighted grading scheme. Something like that might explain why you're looking at this formula. But obviously this is not the standard dot product, because the second component is getting 3 times as much weight as the first in the dot in the formulation, right? But if you check it, it satisfies the needed properties, namely symmetric, additive, homogeneous, and positive definite. So it is an inner product, right? It's an inner product where we would define the length of a vector kind of weirdly, For example, in this inner product, the induced length of the second of like E2 is no longer 1. Like the length of E2 here would be the square root of 3, because the inner product of E2 with itself is equal to 3 in this setup. So, it's a little bit weird. As I was mentioning to you guys, this is the Frobenius norm. And here's the proofs that, in fact, it's symmetric and additive and the rest. Here is this, if we have any set of continuous functions from a to b, we can calculate the integral of the product of the functions like so. And again, it's additive, it's homogeneous, right? All right, so this one actually has relevance to like engineering and science and things. It turns out when you're studying various problems, you end up needing what are called orthogonal polynomials. What on earth are orthogonal polynomials? What would it mean for 2 polynomials to be orthogonal? That's kind of weird. Like, I give you x, you give me x squared. Are they perpendicular? What does that even mean, right? Well, here's what it means. So here, if we look at the inner product based on -1 to 1, we integrate the product of the functions that defines the inner product. So if I calculate the inner product of 1 with 1, I get 2. The inner product with x gives me 2/3. The inner product of x squared with x squared gives me 2/5. So apparently, none of these are unit vectors, right? The length of 1 with respect to this notion of distance is the square root of 2. The length of x as a vector is the square root of 2/3. The length of x squared as a vector is the square root of 2/5. Are they perpendicular though? Well, yes and no. 1 and x, when we integrate that, since we have an odd function integrated over a symmetric interval about the origin, we get 0. So yeah, 1 and x are perpendicular. That's cool. On the other hand, 1 and x squared, well, that's the same as x with x, right? You notice that? Because this is kind of special to this inner product, but if you think about 1 times x squared, it's the same as x times x, right? So the integral of x times x is the inner product of x with x. That's what's going on there. But the larger point is that that's not 0, it's 2/3, which is to say that the angle between 1 and x squared is not 90 degrees. Oh, by the way, you can still define angle between polynomials because we still have the Cauchy-Schwarz inequality, which says that the absolute value of the inner product of x and y is less than or equal to the product of the norms of x and y, which is tantamount to saying that you can assign an angle between them in terms of the inverse cosine of the quotient of the inner product of x and y divided by the length of x and y, assuming x and y are non-zero. So these are not perpendicular, and but x and x squared are perpendicular. All right, great. So guess what? We can do Gram-Schmidt. Gram-Schmidt still makes sense in inner product space. So how's that go? We take the second vector and we subtract off the piece which goes in the direction of the oh, come on. Oh, I guess that's okay. Usually it would not be okay because I'm like, I didn't multiply by my vector here, but what's my vector? The first thing I'm in my list of I'm orthonormalizing. I'm trying to make this into an orthonormal set, right? So my first vector is 1. So there's a 1 here. All right, it's not a typo. So I have x minus 0 is x. All right, so in other words, if I'm trying to orthonormalize the set 1x x squared, the first thing's free, as always with Gram-Schmidt, right? What's a likely question on your quiz Monday? Do you think Gram-Schmidt's on there? I would be shocked if there was not a Gram-Schmidt problem there, right? So that's how we orthogonalize a set of vectors. Now, obviously, this is not on the quiz Monday, right? This whatever happens here stays here, all right? Unless you take 321, in which case, well, then that's a different story. But anyway, so you all should take 321. It's a great course. But although if you take it because you want. Don't do like the engineers used to do and take it because they look at the list of like things they could do for their math minor and like, oh, linear algebra. Algebra's easy. Let's do that. No. Bad decision. And I tried to talk them out of it in the first week back in this world that we used to live in, but they would not listen. And then they would discover it's a math major course replete with the proof expectations for math majors. It's one of like the 3 or 4 courses which forms the core of the math major. So we learn things in there that math minors might not want to learn or experience, depending on your nature. But anyway, it is a good course, but it is a serious course, is my point. So anyway, so this U2 is just x, right? So it's orthogonal. And then U3, I take my x squared and I subtract off the pieces of it, which are in the 1 and the x directions. To pick off the piece that's in the x direction, I have to take x with x squared divided by xx. To pick off the part that's in the 1 direction, I take the inner product of x squared with 1 over 1, 1. Now, x squared with x is 0, thankfully. So this is gone. But we do have to subtract off this, which ends up subtracting a third. So now, basically, here's the deal. The set 1x and x squared minus 1/3, these are orthogonal vectors in the space of polynomials. Of course, it's not normal yet. To normalize it, you have to calculate the length of these vectors. We already know that the length of the vector 1 is actually the square root of 2, and the length of the vector x was the square root of 2/3. So to normalize them, I divide by the length, which amounts to 1 over root 2 for my first vector, 1 over the square root of 2/3, which is the square root of 3/2, times x for the second vector. And because of this calculation right here, the length of U3 actually ends up being the square root of 8 over 45. So, oh man. Well, this should be square root of 45 over 8 here, I think, unless I'm missing something. I have to divide by the length here, right? So that's a typo. I'm sorry. Anyway, these are the first 3 what are called Legendre polynomials. These are typical orthogonal polynomials which appear in the solution sets of very famous problems of mathematical physics. Like if you study the multipole expansion in electrostatics, which is the way that the voltage behaves for multiple charges, right? Like we study mostly the monopole in physics 232, which is just the Coulomb potential. If you put 2 charges, you got the dipole. Past that, there's a quadrupole, right? The formulas for these end up being expansions of like Legendre polynomials. So, and anyway, yeah.
How does it apply to finance?
How does it apply to
Concepts, or is it
finance? I don't know. That's outside my scope. Like I don't know anything about finance. I mean, I guess I should, but I mean, I put money into Bitcoin about when like Trump was elected. So like don't listen to me. But every day I open up the Robinhood app and I put $50 in like the day before or the day after Trump was elected, and like it's been down to like 28, It was at like 35 last week. I don't know. It's kind of. I feel like eventually I'm going to get my money back, but it's going to be some time. I currently hold a little bit of Doge, a little bit of Dog Wi-Fi. Not many people know about Dog Wi-Fi hat. That's a less known one. I got some money in Pepe. I got some in Bonk. And I have significantly more Bitcoin, so that's a little more serious. But yeah, but not like a Bitcoin or anything. I missed my time. If I'd listened to my son and put a bunch of money into Bitcoin when he told me to, I would have much more money now. But anyway, I digress. So there are, of course, applications of all this mathematics to the mathematics of finance. I just don't know those things. Now, the other thing you can do with this is so we have this orthonormal basis for the set of a set of quadratic polynomials, right? Then I could do things like I could ask, what's the projection of the exponential function into the subspace of all functions that's just the set of quadratic functions? Like P2, polynomials up the quadratic order, is a subspace of all the possible continuous functions on minus 1 to 1. And so if I calculate the inner product of the exponential, right, with this basis we just created, which, oh man, I wonder, did I fix that? I'm very skeptical now. I feel like that's supposed to be the square root of 45 over 8. Do I have... Oh, see, this is wrong because of that. Oh, man. Well, I don't know what this means. Well, this isn't exactly right. I need to fix this. Man, that's annoying. Anyway, so modulo my stupid arithmetic mistake there. If we calculate the inner product of the exponential function with v1, v2, and v3 respectively, that gives me the component of the exponential function in the v1, the v2, and the v3 directions, right? And then that gives me the best, if I hadn't made the stupid arithmetic mistake, the best quadratic approximation to the exponential, right? And I don't think this would be necessarily the same thing that you would get from like doing least squares. If you could set up a least squares, like how would you even set up least squares here? I don't even know what that means actually. Like, unless I'm just going to pick like 3 points on the graph of the exponential and use, or more, pick 10 points on the graph of the exponential, look at the model a plus bx plus cx squared, try to plug those points into that model and do the least squares that results from that, right? I don't think necessarily that would give you the same quadratic as this, right? So it's a different notion of approximation than we might get from just ad hoc least squares fitting. Now, what's perhaps more interesting is if we study sines and cosines. So the inner product of, from minus pi to pi is an often thing we consider. If you consider the set of sines and cosines, like 1 cosine, sine 2x, sine 2x, and so forth and so on forever and ever, right? This gives us this countably infinite set of sines and cosines, which are actually orthogonal. Because the integral of cosine and cosine, or sine and sine, if the arguments don't match, it's actually 0. And if it does match, it's pi. In other words, every last one of these guys, except for the first one, has length square root of pi. Now 1 has length 2 pi, so we'd have to normalize that to 1 over 2 pi. So this gives us an orthonormal set of functions, 1 over the square root of 2 pi, 1 over the square root of pi, and so forth and so on. These are analogous to the standard basis, but for the functions going from minus pi to pi. Now, this is the rather bold claim of Fourier, which is that actually this is in some sense surjective. Like if I look at I got to be careful here. So we've defined span in terms of finite linear combinations, right? What if you give up on that? What if instead of saying finite linear combinations, you start talking about infinite linear combinations, right? Series. Well, if you allow yourself series, like infinite linear combinations of these guys, with appropriate coefficients, it turns out that in fact, yes, you can build continuous functions from minus pi to pi using this as a basis of sorts. Again, not quite, because we're extending the notion of span to infinite series. So that is Fourier analysis. This was Fourier's genius idea that you could take any continuous function and build it as a sum of sines and cosines, right? And so here's a picture of it. So for example, if I want to look at like the square wave, which goes 1 from 0 to pi and minus 1 from minus pi to 0, we can calculate the projection of that function onto this space of sines and cosines like this. Like I take f with 1, I take f with cosine t, I take the inner product of f with sine. Now these inner products here are just notations for particular integrals, right? And like the one piece gives me 0. If I take the inner product of the square wave with cosine t, I get 0. But if I take the inner product of the square wave with the sine terms, I actually end up getting non-zero stuff. In particular, if we calculate the integral of the square wave with sine of kt, we get this integral. And I can double up the integral from minus pi, I can trade from minus pi to pi, from 0 to 2 pi because of the symmetry here. I just double the integral from 0 to pi. But remember, f of t is just equal to 1 there. So that's why I have this integral, which then gives me that, which gives me simply it's 0 if k is even, or 4 over k if k is odd. All right? So to do Fourier analysis, you have to integrate. But once you do, you get this infinite series of sines, right? And this right here means almost everywhere. So to be careful about that, you need to study something called measure theory. You can ask Dr. Schmidt more about that. He's very passionate about this topic. He's taught half of a course with me, and we co-taught it like last year. And like he spent his half of the course basically explaining what almost everywhere means and how that ties together actually with quantum mechanics, it turns out. But anyway, so this is like the picture. What's going on here is like the lowest order one is just one single sine, right? And then if you take two sines, you get this kind of green thing. You can't barely see it maybe. But as we take more and more and more, we get closer and closer to the square wave, right? This thing that we're doing, you notice there's like a little bit of an overlap, like a jump over. Anytime there's a discontinuity in the thing you're finding the Fourier expansion for, this is called Gibbs phenomena. If you truncate the expansion before you get to all the way out, there's always an overshoot of about like 10%. So you have to kind of adjust for that if you're doing a numerical method with not keeping everything. So that in a nutshell is what we study in 321. I think the most interesting thing for engineers in all of this really is the Fourier idea, because Fourier analysis is at the base of a lot of what we have technology-wise. Like, for example, music. How do we understand music? Well, music, in a nutshell, we decompose into frequencies, right? Different frequencies, the frequency decomposition is the Fourier decomposition of the musical signal. So basically, you're finding the amount of the music that goes in the different directions of frequency. Inside your ear, there's something like 20,000 hairs. And it's just roughly speaking a picture of it. Like each hair corresponds to a different frequency. So like, when the music has that particular frequency, that particular hair will vibrate, and that's how you hear stuff. Which of course is evolution, obviously, right? But so it's just crazy. I'm sorry, it's just crazy. But anyway, quantum mechanics is at its base a theory about vector spaces. So in quantum mechanics, the states that you consider are the so-called state vectors. These are vectors in an abstract vector space. Now, there's different formulations, like there's a matrix formulation of quantum mechanics due to Heisenberg. There's a function theoretic one that's more to do with Schrodinger. But essentially, the idea is that in quantum mechanics, the wave function has to be an eigenvector. Well, I guess it's not clear yet, but all right, well, okay, so how about this? If this is the Hamiltonian operator, this is the wave function, this is time differentiation. So this is the equation which the the wave function has to satisfy. And typically in quantum mechanics, there is some symmetry that the wave function permits. And because of the interpretations of quantum mechanics in terms of probability, you need this symmetry to be what's called a unitary matrix. And it turns out that in order to have that being a symmetry of the Hamiltonian, you need that the commutator of H in the symmetry is 0. And the proof is right here. If I have that the transformed wave function satisfies the equation, that means this. But since U is a constant matrix, we can pull it out. And over here we have HU. Now, if I know that I'm commuting H and U here. No, I'm not. Over here. What did I do? What did I do? Oh, I used that partial psi partial t is H psi, right? Then, if I rearrange this, I've got H minus times psi equals to 0. But that means that the commutator of H and U, which is with a minus in between, is 0. Anyway, so long story short, the commutator is especially important to quantum mechanics. There's a theorem due to Racah that says for any semi-simple Lie group of rank L, there exist L Casimir operators, C hat lambda, which commute with the whole group, and the multiplets of G can be labeled by the eigenvalues, C1 through CL, because the Casimirs are constant within each multiplet. This theorem basically informs the structure of wave functions in quantum mechanics. It says that to label functions in quantum mechanics, we need these Casimir operators and their eigenvalues. So here's a specific example. A long time ago, people noticed that protons and neutrons were kind of more or less the same. In other words, that protons and neutrons are kind of more or less the same. What do I mean by that? Well, they have nearly the same mass, right? But if you leave a free neutron on its own, after about 11 minutes, it decays by the weak interaction into a proton, an electron, and an electron neutrino, right? And that's actually, and so we say then that there's something called isospin that the neutron and the proton both have, and like the proton has, so like if, in other words, with respect to this T plus and T minus operator, we can rotate in this abstract sense, a neutron to a proton or a proton to a neutron. Anyway, in terms of isospin, the proton has eigenvalue 1/2, the neutron has eigenvalue minus 1/2. So these you're like, what in the world, what's isospin? Well, it's something that nuclear physicists made up to understand interactions that they saw in the so-called particle zoo of the early 20th century. There was pi plus, pi minus, pi 0. These are all nuclear interactions which were observed. Okay, sorry. I'll behave. He probably has a very important engineering presentation he goes to. I didn't see formal clothing, but I don't know. My son brought 2 pairs of shoes with him today. Which is, I don't know, I was kind of remarking that his dress shoes that he's bringing were actually dirtier than the shoes he was wearing because they're very dusty and sitting in the closet. I'm just like, why have you brought dusty shoes to wear to your engineering presentation? I don't understand, but anyway. And why aren't you wearing those shoes? Why are you bringing it? They're uncomfortable, obviously. But anyway, so all of these were observed in nuclear physics, and they all speak to this sort of story time of isospin being conserved. If you ascribe isospin to the pi plus, pi minus, pi 0, and neutron and proton, they play together to conserve isospin in this sense. All right? But in terms of the representation theory, the pi plus, the pi 0, and the pi minus form a triplet with eigenvalues 1, 0, and minus 1 with respect to the isospin operator. Enter the story of hypercharge. So Gelman and Najimi, I'm probably saying that wrong, realized that you can relate the isospin to something called hypercharge, and this is just regular garden variety electric charge. These things are related. In particular, you can show that the neutron and the proton have hypercharge 1, whereas the pi plus minus 0 has hypercharge 0. And if you do that and you graph the known particle content that was seen from the again, the smashing things together in the early 20th century, all of a sudden you find out there's patterns. There's this meson nonet, there's this baryon octet. This is the neutron and proton that you have heard of. These are like higher energy versions of proton and neutrons. And over here, you know, and notice that the graph is hypercharge versus isospin. The question then is, why on earth are these patterns, right? This is really weird. And so in the early 60s, Gelman noticed that if you look at all of these delta particles and the sigma particles, and I don't know what these are, all of this was known from experiment. And there was nothing down here. So in 1961, Gelman predicted that there would be something down here with these properties. And within the decade, in fact, in 1964, that particle was discovered. But at this point, there was no explanation for why these patterns were present in the fundamental elementary particles, neutrons, protons, so-called mesons. Well, the answer to why those are is ultimately given by the representation theory of SU3, which I won't try to explain too much, but it goes back to that theorem of Racah and all that. It turns out that you can build multiplets of S3 by these fundamental triplets, the 3 and the 3 bar, which correspond to what we call a quark or an antiquark. And so you can use up-down strange quarks to build things that have hypercharge 1/3 or minus 2/3, and regular charge, fractional charge 2/3 or minus 1/3, something called baryon number 1/3, strangeness 0 or minus 1, like this. And just to get to the point, you can build those patterns that I was saying from taking what's called the tensor product, which is related to the tensor I talked about in here, kind of. You can fuse two quarks together through the algebra of the tensor product and form the meson nonet. And you can fuse 3 quarks together, similar pictures, and form the baryon decouplet. So through the tensor product of 3 quark states, we can build all of the different possibilities which had been observed in physics. This is why we think quarks exist. It's because through like a couple of simple things and well-defined mathematics, you can build all of the possibilities and the ones, and it covers everything that we observe. So has anyone ever observed a quark? No, like not directly. It's impossible. In fact, this is one of the central problems, is what's called quark confinement. It's a well-known fact of experimental physics that the electric charge of a particle is always in integer multiples of the electron charge. But quarks have fractional charge. As such, they can't be observed. Why is that? Well, there's various phenomenological models which try to put this into play. One of those is the string model. The string model basically says 2 quarks are connected by this string that can't be broken. And if you break the string, then another pair of quarks appears. So they're not isolated. They always come in pairs. This is the early string model for quarks. It actually ended up giving rise to string theory, which is now a theory of gravity and everything. And, well, it's a theory of theories, but it's probably not physical. But it's got lots of good math. So anyway, this seems like a good time to stop. So anyway, this is just to give you a flavor of the fact that vector spaces and linear algebra, there's much more to learn, much more to learn.